we were looking at experimental measurement techniques at micro and nano scale, you know. So, what are all the things that you have to start with is first the dimension of the micro channel, for example, including the surface roughness. So, we looked at some of the techniques there. Then we looked at how do we measure the pressure difference. Okay, so because as we talked about, a considerable part of the differential pressure will include also the expansion and contraction losses. So, therefore, if you want to calculate only pressure difference within the micro channel and not you know, usually we keep the pressure tappings outside the channels. Okay, so, the inlet and outlet ports are the convenient locations to fix the tappings, and unfortunately that includes the additional contraction and expansion losses. So, we have seen a few methods. One is the tube cutting method, where you take the difference between a longer tube and a shorter tube to eliminate the expansion and contraction pressure losses. Okay. There are also other methods of direct measurement of pressure, like using pressure sensitive paint. So, all this I have covered in the last class, and also the optical lever methods. Okay. So, the optical lever method is a more expensive technique. So, you need a laser mechanism. So, this will illuminate the laser onto a flexible membrane made of silicon. So, this silicon membrane is connected to the pressure tappings on a micro channel. So, depending on the deflection of this membrane, so the reflected intensity of laser will have different angles. The deflection angles will be the function of the deflection of the membrane. So, therefore, you calibrate it in the beginning as a function of the deflection, you know what is the pressure. Okay. So, using the calibration you can actually use it you know, in an experiment and get the values of pressure. So, these are very accurate ways of getting it, but of course, you need a more expensive unit in terms of a laser and also a sensor unit which can detect the reflected beam of laser, and the sensor beam also should be on a traverse mechanism which can move you know in different degrees of freedom. Okay. So, we have looked at this. Now, in this today's class we will look at the other two, which is which are the temperature and flow measurements, right. So, at micro or nano scale, you know, nano scale, of course, there is no point in defining or measuring a temperature, but at the micro scale, of course, you know, so when you are talking about conventional thermocouples, you know, you have a junction of basically either, you know, chromium, aluminum. So, you have different thermocouple elements which you make a junction, you create a junction which produces an EMF based on what is the Seebeck coefficient of this particular thermocouple junction. So, that means as a function of temperature you generate an EMF, okay, and depending on the alloy that you have, you know, so you get a different response to temperatures. So, this is denoted by the Seebeck coefficient. Okay. So, now the similar principle can be used also at micro scale, but the difference is that the bead diameter or the junction that you make now should have diameters of the orders of microns. So, otherwise if you put a bulk thermocouple into a micro channel, you are going to intrude the flow. Okay. So, this is an intrusive way of measuring the temperature, which is not preferred. Okay. So, if you put a thermocouple, it is also likely the flow is getting disturbed, flow pattern will be different. So, which you do not want. So, therefore, if you take the case of micro channel of the order of 1 millimeter or less, so the bead diameter has to be quite small, of the order of few microns. So, therefore, there are different possibilities of measuring the temperature in a micro channel, so or any micro element. So, one of the methods is using what is called as a micro RTD. Okay. So, resistance temperature detector. So, you have conventional RTDs. So, it is the same way in a micro channel you can also miniaturize it and you can call this as a micro RTD. The other common method is the micro thermocouple. Okay. So, apart from this you also use what is called as a semiconducting sensors. So, in essentially all of these, the basic principle is you do not measure temperature directly, right. So, unless you have a thermometer is the one which maintains the thermal equilibrium, and you measure directly something in degrees Fahrenheit or degrees Celsius. but in all the conventional measurements that we are using in heat transfer using RTDs or thermocouples or some sensitive paints, temperature sensitive paints, we do not measure temperature, but the response to the temperature in terms of current or resistance or voltage. Okay. So, this is how we indirectly get it, and we know the calibration of the current versus temperature or voltage versus temperature, that is the behavior of how the current or voltage or resistance changes. Sometimes it is a material property, for example, the resistance is a material property depending on the kind of material you choose. So, you know the temperature coefficient of electrical resistance. Okay. The other case you have to do a calibration. So, you know how much voltage will be produced for example, for a corresponding temperature difference. Okay. So, you know the Seebeck coefficient which will essentially define this, and based on that you can calibrate it you know with a standard ice bath where you know the reference temperature, okay, and you can get the values of voltage, right, and so this can be used for other temperatures as well.
So the coefficient of metal itself is a function of the temperatures, and then how it will be measured the temperature?
So, I think this is where the calibration comes into picture. So, you calibrate, that means you know the actual temperature in a, that means you use a bath, you use a thermostatic bath or a constant temperature bath whose temperature is fixed. Okay. So, that is already done by another thermocouple which you know that it is an accurate thermocouple, and you dip this into this reference temperature you know one end, the other can be some ice, okay, which could be 0 degrees, which is always fixed. So, this temperature difference is now going to produce a voltage. So, although you make use of the Seebeck coefficient, this is a function of temperature. So, you just take that information to build materials, a junction of materials, and depending on the operating temperature, therefore, you use different junctions, but during the calibration you do not use this information. So, you actually measure the EMF produced, okay, versus you know what is the actual temperature that is there. So, that will give you the calibration, okay, and now to get back the temperature you now actually sense the voltage, because in the real case when it measures the temperature it is only producing a voltage. So, and from the calibration you invert and get back the temperature, right. So, this is basically the conventional way. We do not directly sense temperature, but indirectly using you know current or change in the resistance or corresponding change in the voltage, and which is quite accurate. So, if you look at the RTD, for example, in RTD you know the temperature coefficient of the electrical resistance. So, therefore, as the temperature changes you know increases, for example, the electrical resistance could increase. So, depending on this calibration you know what should be the change in resistance for a given change in temperature. You know you can draw the calibration curve, and when the actual element, the RTD element senses the particular value of resistance, you know what is the corresponding value of temperature from this particular calibration. So, it is a fairly straightforward procedure. Okay. So, sometimes you do not even have to calibrate, because the value of dt by dr is constant and it is given to you over a temperature range by the manufacturer. He will give you over this temperature range what is the value of temperature coefficient of electrical resistance. So, directly you have to use it and then you know make sure you are within the temperature range, and you can directly get the value of temperature. Sometimes he gives you a table, this temperature, this is the resistance, this temperature, this is the, so you interpolate it, if you get resistance somewhere in between, and you can find out the corresponding value of temperature. So, this is one of the simplest ways to you know get. So, there is no junction formed, it is only a metallic element which has a very high coefficient of electrical temperature coefficient of electrical resistance. Okay. So, the more common ones which are used is platinum, okay, because it also you know it is inert and does not react with most of the gases, right. So, advantages are it is fairly straightforward to fabricate, and it is characterized by a simple linear response like this. So, the same RTD which is used for the macro scale can also be miniaturized. So, we can have a very small sensor probe of the order of microns. So, that fabrication is quite challenging, but once you miniaturize it, it exhibits a similar property. Okay. So, the other one is the miniaturizing the conventional thermocouple. Okay. So, what we call as now thin film micro thermocouples, this principle is the same as the conventional thermocouples. They use the Seebeck effect to measure the temperature of a bimetallic junction. Okay. So, you have two metal elements, they make two junctions. So, one is the sensor where you connect it to the object to measure the temperature, the other is the reference which you keep it in an ice bath or whatever. So, you measure the voltage, correspondingly this will be used to the calibration is used to get the temperature. Okay. Now, the manufacturing of micro thermocouples are more difficult than micro RTDs, mainly because making this junction with the micron sized bead is going to be the biggest challenge. Okay. So, making junction of two conventional materials of the order of millimeters or so, it is quite common, but making it of the order of 5 microns or 10 microns is going to be the biggest challenge. Okay. So, some of the common ones which are used is the chromium film. You have a nickel substrate and you have a chromal thin film thermocouples. So, these are some of the materials that can be used as K type thermocouples. Okay. So, if you want to make a junction of 25 micron by 25 micron, so this is the biggest challenge actually. So, therefore, the principle is similar. You have two metals and you make a junction on one end where this is to be pasted on the sensing side and the other is kept at a reference temperature, but the sensing side should have a bead, a junction which is of the order of maybe 25 microns or 25 less, so this is where the challenge. And also you have to select a material which gives a good sensitivity. This is measured by the Seebeck coefficient. So, that is the kind of voltage that you generate for a given temperature difference. Okay. So, and also the other important challenge with micro thermocouples is the high response time. Okay, very good sensitivity. Very good sensitivity means the response time has to be very fast. It cannot be of the order of standard thermocouples. Okay. Standard thermocouples can wait with few microseconds or milliseconds, but micro thermocouples have to be response to the order of nanoseconds. Okay. So, inherently all these processes at small scales are not only small length scales, but also small time scales. So, so therefore, any attempt to measure the flow or pressure or temperature should also consider this quick response. So, this is another challenge. So, the material selection also depends on not only on the Seebeck coefficient, but also on the kind of response that you get. They should be able to get a response of the order of nanoseconds. Okay. So, the biggest limitation is the fabrication trouble for this kind of micro components, and especially the quality of the surface and micro roughness now will become a big role when you are creating this junction. Okay. The inherent defects in the material and the surface roughness now will get amplified, right. So, sometimes you may not have a perfect junction, okay, and sometimes this junction may not be able to be uniform in sensing a particular temperature. Okay. Some parts may be rough corrugated. So, some parts will have a better contact, some parts may not have a sufficient contact. So, this will again lead to problems in accurate temperature detection. So, therefore, fabrication of micro thermocouple is actually more challenging, but of course, in terms of response time and also the range of temperatures that you use, they are more versatile than the RTDs, because RTDs have a very limited range of temperature. Apart from that, you also have what are called as semiconducting sensors. So, again so this is based on using rather than using metallic elements, you use semiconductor devices where the junction voltage is proportional to the junction temperature. So, at a particular junction, suppose you make a PN junction diode. So, the voltage that you measure across this PN junction will be direct function of the temperature at which you maintain this. So, therefore, you can do a calibration at different temperatures, you can calibrate the voltage that you get, and then this can be used also to measure the actual temperatures. So, this could also be used provided you have a good response, the response time also has to be considerably fast. Okay. So, yeah, so this will kind of complete the temperature measurement. Now, we will quickly move on to the other important component, which is measurement of velocities. Okay. Now, when we talk about velocities, these are not flow rates, because the flow rates are averaged values. So, we are going to look at local velocities, that is the velocity field. So, I mean if you are talking about micro channels, flow patterns of the order of millimeter sized field. So, then that means you have to resolve the field within the order of few microns in order to get the local velocity field, local velocity data. So, therefore, how do you do this? So, then again you have to rely on laser based diagnostics. Okay. So, the more common ones nowadays is the micro PIV, okay, micro particle image velocimetry, and LDA is used. LDA is also an anemometer, but used using a laser, and this is used for larger channel dimensions, but if you are really looking at small channel dimensions, we have to look at the same PIV which is there at conventional measurements, and this has to be scaled down to capture micron sized resolution. Okay. So, apart from that you also have a expensive method called the molecular tagging velocimetry. So, I think many of you know how the PIV setup works, right. So, it is basically you should have a experiment which is optically accessible first of all, and that means you should be able to have construct optical access from where you can put the laser source from one end, and the other end it should be able to be captured by a high speed camera. So, it should have optical access for both the laser to penetrate the system and also for the light which is scattered and coming out of the system to be captured by a camera. So, it should have a two-way optical access, number one, and number two is it should also have seeding particles which are of negligible density, okay, compared to the actual fluid of which you are measuring the velocity and so on. If the density is high, then this will have its own momentum which is different from the that of the parent fluid, and therefore, this will not give you an accurate velocity field. Okay. So, therefore, it should be quite light. At the same time, the property is it should be luminescent. That means, once you radiate it with a laser of a particular wavelength, it should start glowing, right, which should be captured by the high speed camera. So, apart from that, the principle is very simple. You just add these tracer particles into the main element, fluid element of the system. So, you add several millions of these particles into them, and then you just keep pulsing the laser. So, pulsing the laser, so you have to have a pulsed laser. So, every few nanoseconds or microseconds depending on the time scale, you pulse it, and this will correspondingly respond by glowing. So this glow will give you the track of the particles. So, you keep recording the images with a CCD camera at different time intervals, every few microseconds or nanoseconds, and by looking at the snapshots in time. So, you have one image where a particular particle would have been at a location position vector xt. Okay. After time delta t, this particle would have moved x plus x at t plus delta t. Okay. So, by just simply taking the two images, looking at the position vector of the particle at t plus delta t and particle at time t, you take the difference between them divided by delta t should give you the velocity magnitude, right. So, this is a very simple method, like that you look at each and every particle and you will be able to calculate the corresponding velocity vectors. So, that means you have the local velocity vectors all over the entire system. from these images. If you need a 3-dimensional snapshot, then you have to have a holographic PIV. That means you should have 2 cameras taking a 2 different planes, okay, so that you can construct a 3-dimensional motion of this particles. So, that will give you a complete 3-dimensional velocity field. So, but basically this is the principle, and in the case of micro PIV all this has to be much more smaller. Your tracer size should be now really small, number 1. Number 2, again the response time has to be very quick, and again from the laser side point of view also the laser pulse width should be now really small, and the camera point of view it has to be a really high speed camera to take images at very high frames per second. So, therefore, all of these now become technologically more demanding. Okay, for example, if you are talking about yeah, so let us look at the comparison between a conventional PIV and micro PIV. So, in the micro PIV you are looking at a field of view of the order of 30 to 300 microns compared to conventional PIV which is covering 30 to 300 millimeters. Okay. So, the interrogation cell is this particular unit cell across which you are tracking a particular tracer within a delta t. So, over a delta t this particular tracer can move from one point to the other within that interrogation cell. Okay. So, if your interrogation cell width is too small, this will escape the cell within delta t, or if your delta t is too large also we will not be able to capture this tracer within that particular interrogation cell. So, therefore, the interrogation cell size also has to be very small in order to resolve the local velocity data more accurately, and therefore, the particle diameter has to be even smaller than the interrogation cell size, right. So, that means you are talking, if you are talking about an interrogation cell size of 2 to 20 microns, your particle diameter should be of the order of 0.3 to 0.7 microns, less than a micron. You are talking about 300 to 700 nanometer particles. These are nanoparticles essentially, right, whereas in the conventional PIV you are looking at micron sized particles. So, for one they will be not too much affected by gravity because of inherently very small particle size, but at the same time you need a smaller interrogation cell, you need a smaller field of view, and also the laser thickness, the laser sheet should also be very small. So, here it should be of the order of a micron. For example, in the conventional case the laser sheet thickness should be of the order of millimeter, and also the pulse of the laser also should be considerably smaller. Okay. So, therefore, so in the case of, so this is how the typical micro PIV arrangement can be used. So, you have a laser which goes through optics which will make this the laser is actually a point source. So, this particular expanding optics will convert this point source into a sheet of light. Okay. So, this is a beam expander. So, this sheet is sent through a filter cube, that means it is just going to change the angle of this beam by 90 degree. Okay. And you have a microfluidic device sitting at the bottom, you pass the sheet directly through this device. Now, this will interact with the seeded particles inside the device, and there is a camera sitting right at the top. So, this will take the snapshots of the seeded particles, okay, at regular time intervals. Okay, this is basically how you have that. You have a laser, you have the optics, you have the CCD camera, and your system also should be seeded with this kind of nanoparticles. Okay. So, therefore, so there are so many problems just simply scaling down the conventional PIV. So, all these limitations list these problems. For example, you need very short times between pulses and short pulse lasers. So, therefore, the cost goes up. You need a high short pulse laser, you need also a very high speed camera, you need a specialized nanoparticle tracers. Okay, you need also good optics which can basically convert this sheet into a much smaller beam. So, all of these together will make your cost definitely much higher than a conventional PIV. Okay. So, a conventional PIV itself is quite expensive, it is not very cheap. So, on top of that the micro PIV will also make it more expensive. So, apart from this there is also a method called molecular tagging velocimetry. So, this is similar to the PIV where you have tracer particles, but in this case you use the molecules of the working fluid itself respond to the incoming laser pulse. Okay. So, that means pulsed laser is used to tag a region. So, if you have a system, so this you use one of the lasers as a tagging laser and you mark a region over which you want to calculate the velocity field. Okay. And then you have a imaging laser. The imaging laser is now going to send a sheet beam of light through the tagged region, and the molecules there will now change their color in response to the incident laser, and then you use this as a signature to track the velocity vector of these particular molecules. Okay. So, it is similar except that you do not use a tracer here. Okay. So, you use the molecules of the working fluid themselves as the elements to trace the fluid velocities. So, the advantage is that where you cannot use the conventional seeding particles, you use this, but of course this can be used only for liquid flows, because most of the liquid molecules are more responsive to the lasers, whereas the gas molecules are not. Okay. So, and again so that was with the velocity. Now, coming to the flow rate measurements, the flow rate is like you connect a flow meter somewhere at the inlet or the exit to measure the actual flow rate. Now, even that is challenging, because now you are talking about flow rates which are of the order of less than 10 power minus 8 kgs per second. So, very small flow rate, sometimes it is like a trickling flow. So, how do you resolve such small flow rates with mass flow meters? Okay. So, therefore, there are different methods which are used. So, there are indirect methods to also check the mass flow rate. So, what is commonly done is you sometimes weigh. So, you collect the amount of flow in a small beaker over a period of time, and then you check the weight, the difference in the weight, and then you know how much volume is actually flowing. Okay. So, this sometimes may be more accurate than putting a mass flow sensor, because the order of mass flow rates is so small that instantaneous flow rates may be very difficult to detect, but over a period of time, once you let it collect to the order of a few milliliters, then from that judging what is the flow rate might be more accurate. Okay. So, it is not very uncommon for people to just rely on very simple methods like collecting in a beaker over a period of time to calculate mass flow rates, rather than using expensive mass flow meters. Okay. So, all these are with respect to the micro channels, where you look at the fluid pressure measurements, temperature measurements, flow rate, velocity measurements, and so on. Now, if you go to the nano scale, so we are interested in the thermophysical properties, right, such as the thermal conductivity, heat capacity. So, these are things which are required for you to for example, solve the Boltzmann transport equation, and therefore find out what is the size effect on thermal conductivity. So, you have the bulk thermal conductivity, so you use that to calculate the relaxation time of the phonons and so on. Then you use the Boltzmann transport equation, then find out at the reduced size what is the effective thermal conductivity. Now, how do we verify this? How do we verify the value of thermal conductivity coming from the solution? So, you have to also have experimental methods, then only you can verify your theory, right. So, and very small nano scales, nanometer sized films, you cannot measure thermal conductivity the way you measure in a conventional setup. So, one of the most common ways of doing is called guarded hot plate technique. So, it is a steady state measurement technique where you simply sandwich the material between two metallic junctions. So, one at a high temperature, one at a low temperature. You measure the temperature difference, you measure the heat flux, and you know what is the effective thermal conductivity, right. So, on one side you basically know what exactly is the flux, heat flux applied, okay. The other side you maintain at a constant temperature. So, therefore, the temperature difference now will be a function of the thermal conductivity. So, then you measure the hot side temperature, cold side temperature, heat flux. So, then from using the Fourier's law you can directly estimate thermal conductivity. But when you go to nano scales, you cannot measure temperatures. So, nano films, thin films. So, therefore, how do we indirectly measure thermal conductivity without measuring the temperature is actually the challenging part. So, for this one of the most common methods which have been proposed by David Cahill in the 90s is called the 3 omega method, okay. So, the 3 omega method is a very novel innovative technique of measuring thermal conductivity of either it could be a bulk material or a nanoscale material without having to measure any temperature, okay. So, I mean so if you generally look at the thermal conductivity measurement techniques, either you can do measurement at steady state or transient. So, the steady state method is one of the methods I described is the guarded hot plate method. The transient method includes the transient hot wire method. The hot wire method was the one I talked about in the nanofluids, okay. So, when you immerse a probe lines pointed line sensor, heated sensor into the nano in the fluid and you actually look at the response over a period of time. So, how the temperature of this probe changes, okay. So, depending on that you can find out the thermal conductivity of the liquid, okay. Now, when it comes to nanoscale films, so even this method cannot be directly used. So, therefore, the 3 omega method is used, and this 3 omega method falls under transient measurement category. So, it is not a conventional steady state method. So, how does this work? So, for example, for this we have to do some photolithography. That means you have to carry the sample to a MEMS lab where they have this photolithography machine. So, you have to prepare a mask and then you have to etch and then you have to deposit some gold film. So, finally you will get what is called a 4-point probe, okay. This 4-point probe will have 4 contact pads. So, across 2 contact pads you basically supply the input current, that is I at a particular frequency, okay. And so, this is basically the supply pad, okay. So, there are 2 more contact pads from which across which you measure the voltage, okay. So, therefore, the same probe acts like both like a heater as well as a sensor, just like your transient hot wire. The hot wire also it was heating at the same time, it was also sensing the temperature. The same way this 4-point probe itself acts like a heater. Now, when you are supplying the current through 2 ends of this probe, so you are actually raising the temperature because of the resistance is going to heat the surface of this particular substrate, and this will cause a change in the temperature over a period of time, and this will now induce voltage across the other 2 contact pads. So, the concept is if you are supplying current of frequency 1 omega, that is basically some frequency, the temperature response will be according to I square, okay, which is of the order of 2 times omega, and the resistance will also be changing as a function of temperature, which is also 2 times omega. So, now when you take a product of I into R, okay, so therefore, you are talking about 2 components. So, one can be 3 omega, one can be 4 omega. Now, what is special about this 3 omega component is that if you extract the 3 omega component, so it will directly give you what is the temperature rise at the surface of the material, and directly you can calculate the thermal conductivity with that particular value, okay. So, therefore, if you take the product of I into R, so you have components which is coming from omega here and the component which is coming from 3 omega. So, only this amplitude of the 3 omega component is called the V3 omega, okay. This is the voltage corresponding to the third harmonic 3 omega. So, we take the measurements at 2 different frequencies. So, one at say omega 1, we supply a input frequency omega 1, we measure V3 omega 1, then we supply another frequency omega 2 corresponding velocity at 3 omega at the second frequency, and then we take the we use this particular expression. Dr by dt is nothing but the coefficient of resistance to temperature. Okay. So, based on this you can directly express what is the thermal conductivity of the bulk film. So, this method is a method which is used for the bulk films, that is of the films of the order of say micron sized and above. But what if you really go to nano scale? So, how will you modify this setup? So, for that you have to deposit this nanoscale film, which is called the thin film here, onto the top of a bulk material which is electrically insulating. Okay. So, also the film, that sample that you are measuring should also be kind of electrical insulator, otherwise what will happen is, apart from the heat conduction, you will also have electric conduction through the film, and this will corrupt the data. Okay. So, now for thin films, what you are going to measure is a kind of a total temperature rise for both the film as well as the substrate, and you have to subtract the contribution of the substrate, because first you do the experiment for the substrate like this, you know what is the temperature rise for the substrate, and now you do the experiment for both the film along with the substrate, you know the total temperature rise. So, if you subtract this, this will give you temperature rise only due to the thin film, from which you can calculate the thermal conductivity. Okay. So, this is how this has been adapted for thin films. Now, we can also use this to calculate another interesting thing, which is the thermal interface resistance. So, if you have a sandwich of metal and a semiconductor, there is a temperature drop at the interface of these two different materials. So, we can use the same method, extend it to also calculate the thermal resistance of multiple materials. Okay. So, we have done some of these measurements at our laboratory at room temperature as well as at room temperature as well as at elevated temperatures, and this kind of gives you an idea how the thermal conductivity varies as a function of film thickness and also as a function of the temperature. So, we have some standard experiments, experimental data available in the literature, and our student Samskar and Sriniket, so they have independently carried out measurements. So, you see very strong size effects. As the size of the film becomes smaller and smaller, the temperature, the thermal conductivity drops, and depending on the kind of preparation of the sample. So, you may have two different values of thermal conductivities, So, the bulk values themselves are quite different. So, at film thickness of 1000 nanometers, you see these two values are quite different from each other, whereas at the nanoscales they both converge. Similarly, they also exhibit strong functional dependence on temperature. Okay. So, for a given sample, for example, if you have 100 nanometers and 500 nanometers sample, so they display different dependence on temperature. Okay. So, all these can be measured using this method very accurately. Okay. So, also this can be extended to measure the thermal interface resistance. We have done some measurements where we have chromium sandwiched between two silicon dioxide substrates, and also for silicon sandwiched between two silicon dioxide substrates. So, we have got the values of thermal interface resistance. We have compared also with the order of magnitude with some measurements before. Okay. So, finally, so after doing all these measurements, a very important analysis is called the uncertainty analysis. So, you have to tell what is the confidence of your experiments, confidence level. So, your experiments are never 100% accurate, because they all come with uncertainties in every stage. So, it could be uncertainty with your probe or the uncertainty in the setting itself. Okay. For example, if you take friction factor, okay, now friction factor, if you want to calculate from experiments, so what are the things that you have to measure to calculate friction factor? So, one is your pressure drop, okay, the other is your velocity, the other is your density, and the others are your dimensions, length and diameter. Okay, at micron size, now the uncertainties associated with even calculating dimensions become more, because you are dealing with micron size diameter. Now how accurately are you going to measure that? So that is what we had seen in the first part, how to calculate the dimensions accurately. Okay, you have to use one of the methods, but this method itself will have a certain uncertainty. Okay. So you have to know what is the uncertainty of measuring each parameter, such as length, diameter, pressure drop, density, velocity. So independently you measure each of that, and you should know what is the uncertainty, and then from this we use the procedure called the uncertainty analysis to calculate the global uncertainty in friction factor. Okay. So the method is pretty simple. If friction factor is a function of parameters x1, x2 up to xn, so the absolute uncertainty in friction factor is the sum of the squares of all the individual uncertainties multiplied by the derivative of this particular factor on that parameter. So for example, if you know df by dx1, you take the square of that, multiply it with the square of the uncertainty. So you sum them over all the uncertainties and then you take square root. So this will give you the absolute uncertainty. Okay. Now for the friction factor, so this is a function of your length, your diameter. So it could be a function of temperature, it is a function of delta P, it is a function of for example pressure losses at the outlet, it is a function of mass flow rate, because mass flow rate is related to your velocity. So out of which you can rule out, so you can give weightage to certain factors. For example, if you feel that there is no dependence on temperature, you can give that coefficient to be completely 0. Similarly with the pressure at the outlet, so you can give that to be completely 0. So you can give certain weightages which are called sensitivity coefficients to certain parameters more than the others. If you feel that this parameter plays a much bigger role in determining friction factor than the other. Okay. So, so therefore from the absolute uncertainty we can write down an expression for what is called the relative uncertainty. So this will tell you what is the percentage uncertainty in determining friction factor. So it could be plus or minus 5 or 10%. So when you say plus or minus 5 or 10%, this is usually relative uncertainty. So at that particular value, you basically multiply that value by plus or minus 5% of that value. So that will give you the uncertainty, right. So that will be finally, if you calculate, it will come out to be nicely a function of each parameter's uncertainty divided by the value of the parameter square, sum over all the parameters and take square root. So that will give you the relative uncertainty. Okay. And you can also give a weightage by including these sensitivity coefficients if you want to give more weightage to one parameter than the other. So this is a standard procedure used across all measurement analysis. The uncertainty is a very important thing that you have to report. When you do measurements, you have to say what is the confidence level of your measurements, whether it is within plus or minus 5% or within plus or minus 10%. So that will give you the error bars. So you also plot your data with these error bars. Sorry. So you also plot these error bars, and then when you plot these error bars, you present to the research community that yeah, I have done these measurements, but these measurements are not 100% accurate, but could be accurate anywhere between these error bars. Okay. So this kind of completes what I wanted to talk about measurement techniques. So I hope with this you understand at least some important measurement techniques to be used at micro nano scales. Okay. So with this we will conclude this particular lecture and also the course. If you have any doubts or so, you can email me. Thank you very much.